My name's Anders Learmonth, and I've just completed my MSc dissertation at Staffordshire University. I'm going to be talking today about my project, which was using blockchain in a decentralized manufacturing execution system, or MES, to improve the data integrity. So for a bit of background, within manufacturing, any military, aerospace, and healthcare products require complete and reliable traceability of all actions taken against them. Manufacturing execution systems are responsible for this tracking. Operators must use this MES to record any actions taken and any defects that they've found or have reworked from others. Reports can then be generated to show an overview of historical actions and quality metrics, as well as who completed each action and when they did it. The problem with existing systems, including these MESs, is that the database can be retrospectively modified by anyone with the appropriate permissions. A solution should be found that ensures reliable and trustworthy data collection and export is achieved within MESs. So I began by researching what has already been done in this area. A common theme in my literature review was studies mentioning a trust deficit in modern systems. This is where people cannot be trusted to perform the tasks consistently, ethically, and reliably, whether this is their intention or accidental. It's been proposed that there should be as little trust as possible placed in the hands of any external components of a system. This can be end users, third-party tools, or administrators. A zero-trust model should be adopted for these trust-critical systems, where nothing external is trusted by default, and any requests made or data will be verified first. Many reports suggested that blockchain could be used to bridge this trust deficit, largely because of how it works is very similar to the zero-trust model, by providing better auditing and visibility to the entire network, including transparency of all historical data changes, significantly increased difficulty to create fraudulent actions, and the ability for any user on the network to audit each other. And despite blockchain appearing as the ideal solution to this problem, there is no currently available MES which provides a completely trustworthy dataset. Continuing my secondary research, I looked into any projects that have had historical success using blockchain in their applications. Bitcoin is a well-known cryptocurrency that uses blockchain as its underlying technology. This has seen global success and has been adopted by many companies across multiple industries. The double spend problem in cryptocurrency is where the same coin can potentially be spent twice before the network is updated to realize that it's already been spent by that user. Nakamoto solves this by essentially slowing the entire network down using a proof of work method which forces the client adding the transaction to complete a task which is known to take a varying amount of time depending on the total size of the network at that moment. The white paper goes on to explain the use of public and private key pairs to ensure that the user claiming to add the transaction is valid and it is actually that person. It would be impossible to add a transaction to the blockchain ledger without having access to that particular user's private key. The Georgia Land Registry is another good example of where blockchain has been used to solve a problem in the real world. In this situation, corrupt authorities were stealing land by fraudulently editing the registry. So they were taking land from the residents and updating the name against them in the existing registry with either their own names or the names of people that bribed them. However, a blockchain subsystem was added purely for the data storage, which allowed any citizen of Georgia to log on at any moment in time, and they could see any historical changes and flag them as fraudulent. The addition of this subsystem completely eliminated the problem of historically editing the registry database entries. A negative side of blockchain that kept appearing in my secondary research was the idea of poor scalability and poor performance. This can be due to the single master blockchain having an endless number of blocks added to it, and eventually when it comes to making use of this data, the client will have to cycle through every single block in the blockchain to get some useful information at the end. Dr. Gideon Greenspan in 2015 suggests splitting out these blockchains. Rather than having one master blockchain with endless results, you would have a separate blockchain which only accounts for one particular entity. This can help with scalability and performance as we continue to add individual blockchains to the master data set, rather than more blocks to the single blockchain. Based on my research, I identified that there is no currently available MES which can provide 100% reliable and uncorruptible data collection and export due to the ability to retrospectively modify database entries. My research question for this project is implementing blockchain and decentralization into an MES a viable technique to improve the trustworthiness of the data? And my aim builds on this by listing the actions that I will be taking throughout my project in order to answer the question and fill the research gap. The words in bold become my objectives, and each of these objectives will be met by deliverables, which I'll mention later in this presentation. These objectives can be summarized by their keywords, and with each of these task categories, I can fill out some tasks that will allow me to achieve each header, enter their start date, duration, and completion date, and plot these onto a Gantt chart. Following this Gantt chart allowed me to stay on track throughout the project and clearly see all outstanding tasks required for its completion. I began primary research with the goal of proving or disproving the requirement for a solution to this problem. I decided to use a questionnaire with 11 mostly multiple choice questions using the Likert scale based on strongly agree to strongly disagree options. I distributed this in paper and digital forms using Google Forms to help reach the maximum sample size. Before sending out the final questionnaire, I piloted it with 2 people to get their initial feedback. Based on this feedback, I added a background section with a few questions to find out about the participants' history with MESs, and I added a free text question to allow them to elaborate on any previous answers. I received 17 responses and analyzed these using SPSS, with the result showing that 13 out of the 17 participants did not trust the data exported to be accurate, and with only 23.5% feeling that MESs are somewhat trustworthy overall. With these results, I concluded that a solution is required to improve the trust in the data, specifically within MESs. The final 2 questions in the questionnaire asked about routing modifications during WIP. This is the idea of adding, removing, or modifying the order of actions taken against a product to complete its build. The responses to these questions and also the free text answers supported the idea that it should be easier to modify a routing within MESs, where currently these are locked. I adopted the spiral software development lifecycle, which allows continuous improvement as the project develops, with each iteration consisting of the design and code, then the implementation, testing, and review, before starting the next iteration to add new features and to address any bugs found in the previous version. I then created the design documents, including activity diagrams, analysis models, sequence diagrams, and the class diagram for the overall application, where the application is split into 2 main modules, a communication layer which handles the blockchain and the decentralization of the network, and the front-end sample MES for the user interface. These are connected by an API. I used a web-based technology stack for this project, including PHP, largely for its built-in development web server, which is used for the Gossip protocol. I ruled out Python and C++, as the goal was always for a adaptable, lightweight artifact that can be applied across multiple projects in the future. The first iteration of the Spiral SDLC saw the Gossip network being set up, where an unlimited number of clients were able to connect to a known peer, and where every client would periodically receive updates from each other client that it knows of to update its locally stored dataset of blockchains, where every client has an exact copy of everyone else's data. There was the ability from the user interface to add, undo, and view transactions and defects, edit existing defect statuses to record when a defect has been reworked or inspected, and also the ability to remove an operation from a routing based on the requirement gained from the final two questions in the questionnaire. During the testing of iteration 1, it was found that in certain situations, some transactions would be lost. This was later found to be when the user adds a new transaction or change to existing transaction at the same time as receiving data from an external client. I got around this by implementing lock files, which would temporarily pause the Gossip protocol, which would pause receiving data from external peers. And this has fixed the problem. I added the use of Bootstrap for faster development of the front end, and a CSS normalize to improve cross-browser visual consistency. System logging was added, which records any time that the data updates, saves, or is broadcast to the network, as well as some key actions taken within the sample MES. This helps with debugging of future issues. The final part of iteration 2 was to grant the ability to add new operations to routings during WIP. So now users of this sample MES had full control over which actions were required for each new product. In order to prove that this project was a success, it required testing and validation. The standardized test plan that I used consisted of 49 test requirements, and these were met by 43 test cases, using normal, invalid, boundary, and special cases. A large number of these were automated using PHP unit tests and Selenium browser tests. Where automation wasn't possible, the manual tests were carried out. After iteration 1, 93% of the tests passed, and after iteration 2, 100% of the tests passed. Further validation was gained through undertaking 2 interviews, and when these interviewees were asked would they trust data from this system more compared with available alternatives, the responses overwhelmingly supported the success of this solution. Both interviewees, who work with manufacturing execution systems on a daily basis, mentioned the addition of a dashboard page, which is built into the application and would provide top-level data representation and the ability to drill down into these top-level graphs to view the data. This can be considered for future development. So in critical evaluation, this solution improves trust by holding all network users accountable and by allowing them to audit each other, disregarding any invalid data. It builds on existing work in this domain and is based on requirements gathered from secondary and primary research. It provides a proof of concept that can be built upon and adapted for other trust-building projects in the future. Some of the problems encountered during this project was where the application was visually appearing different when viewed on different browsers. This was fixed by applying the CSS normalize and improved overall consistency. Some transactions were being lost in a specific case within the application, A specific condition was causing loss of transactions when adding a new transaction from the software at the same time as updating from a peer value. This was resolved by adding .lock files, which temporarily block the peer updates. Consideration in future projects could be given to use a different method to proof of work, which has seen criticisms due to its higher energy and computation consumption than some available alternatives. Some that could be explored are proof of burn and proof of stake. There's also the opportunity to reduce the required minimum system specs, where currently all users require PHP to be installed locally in order to start the development server, and initially a Linux operating system due to the execute permissions required out of the box. A dashboard page was also requested during the interviews. This could be explored for addition in a later version. And due to the smaller sample size of just 17, it may be worthwhile expanding this to reach a wider audience and potentially bring in some new requirements. So in conclusion, this project successfully implements blockchain into a decentralized proof of concept MES and has been externally confirmed to improve the trust levels in the stored data, therefore achieving the overall project aim. And this project aim has been satisfied by these objectives, with each objective completed by producing its deliverable. For example, the objective to research blockchain's usage for increased trust is met by the deliverable, which is the results of the literature review. There are future development opportunities for either myself or other researchers with exploring alternative approaches for better performance or scalability, as well as to reduce the minimum system requirements of this solution to help reach a larger audience. I believe it should also be considered to work towards lights out manufacturing, which is the idea where human operators would be replaced by robotic counterparts within repetitive or dangerous manufacturing situations. This idea synergizes well with this project by providing with both more reliable build and traceability. And finally, when compared to alternative solutions, the responses in both interviews were that current systems do not provide adequately trustworthy data output, whereas this blockchain implementation does, and that this new trust level should be considered as the industry standard moving forward.